H, H, minus. So the H bond, right? So this is coming from that pair of electrons. We'll go and attack the carbonyl carbon, kick up the electrons. So from here, you get the alkoxide intermediate, and then that's going to pick up a hydrogen to finish. Nothing crazy there, right? Okay. So down here, just to show the mechanism for this, it looks exactly the same. You're replacing aluminum for boron and lithium as your counterion, but it's going to behave the same way, where one of the hydrides is going to take the pair of electrons, add in, kick up the pi bond up onto the oxygen. That's going to give O minus, with the H in there. And then, just like up above, the O minus alkoxide is going to go and pick up a proton from the water. Fair enough? Questions about that? That's really all of the scenarios that you're going to have to really deal with for aldehydes and ketones, right? With the hydride source. And again, for those, interchange aluminum hydride or borohydride, as you wish. Okay, there's no need to worry about it. Okay? So that's the nucleophilic addition part of the stuff. These things can also do nucleophilic acyl substitution. Okay? So when you do the acyl substitution, I'll use the acid halide as the first example. These can be done with essentially acid halides, anhydrides, and esters. Okay? So the leaving group here, in this case, is a chlorine, so that looks more like a traditional leaving group that you guys have seen. But you can also do it with an ester where you have an OR group leaving, or the anhydride where you have a carboxylate ion leaving. Okay? In terms of reactivity of these things, the acid halides are the most reactive. Okay? It's got that good leaving group attached. We'll get into some more of the reactivity of these kinds of things when we get to chapter 22, I think. That's the carboxylic acid derivatives. But what happens here is if you treat this with NaBH4 followed by HCl or water, whatever you choose, doesn't matter, okay? This will do the acyl substitution first, to make an aldehyde. But if your hydride source has multiple hydrogens present, then it can actually continue and do a nucleophilic addition in a subsequent step. Okay? So when you have these reactive things like sodium borohydride, lithium aluminum hydride, they got multiple hydrogens on them. Okay? And I'll show the mechanism for how they deliver the second hydrogen, but ultimately this is going to go again and do a nucleophilic addition with this guy. So at the end of the day, you end up delivering two hydrogens and get the primary alcohol. I can put down here OR as a potential leaving group as well. All right? So the mechanism gonna start exactly like we did over here. Okay, so you add in, you kick up the electrons. When you do this, you make the tetrahedral intermediate, O- with a hydrogen and a chlorine. So now, once you get that alkoxide, because you have a good leaving group attached, it can kick back down and push out that leaving group. So this pair of electrons will come back down and push out, and that gives you your aldehyde. That's the ACO substitution part of it, okay? So you could assume that there's excess of the sodium borohydride, okay? But you don't need to put in multiple equivalents of the sodium borohydride because it's got the extra hydrides already attached. So you'll see that the stoichiometry of this is essentially one of these can react with 4 of these to make 4 products. Okay? And we do a lab where we do reduction of a ketone where you guys will actually add in a molar deficient sodium borohydride, right? Meaning that there's, you know, in the sort of stoichiometry of it, there's less moles of it, but it's still in excess according to the hydrides, all right? We'll get there in a couple weeks, I think. But in any event, the product that happens after this is you end up with BH3, okay? BH3 is a Lewis acid, okay? It's a lone pair acceptor, meaning that when you get to this step, this can coordinate to the boron, okay? So that just makes a Lewis acid, Lewis base pair. And hopefully you can see that this brings in those extra hydrides close by to this carbonyl and helps it to sort of deliver it. So that hydride gets delivered in that fashion. O-, H, H, and then proton from HCl gives the final product. I think I gained a So it's got that little twist to it where the boron is going to coordinate. If you forget that part of it and you just bring in another sodium borohydride with like you did up above and do the nucleophilic addition like we did over here, that's fine. But try to do it this way, okay? Everybody good with that? So when you get into doing esters, and esters are going to be a little bit less reactive, right? Okay, because what's a better leaving group, chlorine or O-?
Oh.
Chlorine, right? That's way better leaving group, right? We never do an SN2 where we kick out an O-, right? So that O- is not a very good leaving group. So when you do esters, it's probably better to use lithium aluminum hydride instead of sodium borohydride because it's way more reactive. Okay? So when we talk about amides, okay, which is the C double bond O with the nitrogen, they actually require the use of lithium aluminum hydride, and they do something a little bit different. But it's, if you treat an amide with sodium borohydride, nothing happens. Okay? And we'll talk about that in a minute. Okay, so again, when you get into esters and amides, best to use lithium aluminum hydride. And you know, if you're doing a synthesis problem, you could use lithium aluminum hydride for everything, and it's fine, right? So you don't have to worry. All right, is everybody clear on this mechanism? All right, so if you remember last time, I showed you guys a couple other sources of H-, the dival H and the lithium OT-butyl thing. Okay, so those are important in this context because they have only one hydride that can be delivered, right? And inherently they're a little bit bulkier and a little bit less reactive, okay? So if you want to stop at the aldehyde, you got to use one of those other hydride sources, okay? So if you want to stop it, we'll do a little different. Here's an example. You would have to either use the Dival H or the lithium aluminum tri-T-butoxy hydride. So I don't think I showed you what Dival H looks like, but it's an aluminum with di-isobutyl. So that's your di-isobutyl aluminum hydride. So I'm not going to show it like this, okay? But it's going to behave pretty much exactly like this, okay? I'm going to simplify it a little bit just to make your lives a little bit easier. But just like the boron can coordinate, so can the aluminum, okay? But ultimately, it's going to take this pair of electrons, deliver to hydride, kick up, make the alkoxide tetrahedral intermediate. O minus, HBr, and then just like we've done in the past, kick down, push out the leaving group, and you're done. So that's the straight acyl substitution, and then it's done. Okay, the other reagent is this guy. This is what I wrote as LiAlO-T-butyl-3H. So hopefully it's obvious, but if you want to do this one, you're using that pair of electrons instead, okay?
Where's the negative entity on that aluminum?
So this one is not, right? So there is no negative part of this one, okay? It doesn't have an extra bond to the aluminum. And that's why I said it actually behaves more like this one, where you would actually have the aluminum coming by and coordinating, where it would look kind of like